In this lecture, I'm going to be talking about another article about few-shot learning, but we use contrastive learning for that. So I'm going to be focusing on this paper in 2023. And this is a great paper from Monash University. Very great researchers. Professor Hafari. So few-shot class incremental learning presents the primary challenge of balancing underfitting to a new session's task and forgetting the tasks from previous sessions. To address this challenge, we develop a simple yet powerful learning scheme that integrates effective methods for each core component of this few-shot class incremental learning network, including feature extractor, base session classifier, and incremental session classifier. So we have three core components. In feature extractor training, our goal is to obtain balanced generic representations that benefit both current viewable and unseen or past classes. To achieve this, we propose a balanced supervised contrastive loss that effectively balances these two objectives. In terms of classifiers, we analyze and emphasize the importance of unifying initialization methods for both the base and incremental session classifiers. Our method demonstrates outstanding ability for new task learning and preventing forgetting on these datasets with significant improvement. This is the schematic explaining the objective of losses that are used during the feature extractor training. As you see in A, it classifies losses. Each class has a classifier. So the features of each class are aggregated to corresponding classifier. That's the X mark here. You see X mark. And in B, its contrastive losses. Its multi-viewed batch is composed by adding augmented images to the original batch. Each box describes the composition of multi-viewed batch when the anchor image is chosen. Then positives are aggregated to each other while negatives are dispersed away. So the problem with train set of session T, because we have a set of sessions, for session T, we have this data set and train set of session T. So this one consists of class labels. And N is the number of classes in session T. So the different sessions have no overlapped classes. So this is important that the sessions, there is no overlap. And test set of session T is composed of class labels. For convenience, we denote Cij. So for NVA K-shot setting, so you are familiar with few-shot learning setting, and so, but feature extractor is expressed as F sub C sub theta, and theta is just the parameters of your network. The input is encoded into RD, embedded space by passing the feature extractor. Each class has a classifier for the classification. So this is the overall schematics of the proposed method. The feature extractor is pre-trained to achieve generic representations using the massive base training set. Augmented or having the same label with anchor images are set as positive and else are set to be negative within the batch. Then the model is updated based on the contrastive loss. To emphasize the effect of augmented images, we proposed balanced supervised contrastive loss. For each image within the multi-viewed batch, previous approaches denote the images with the same class as anchor as positive and the rest as negatives. So we further split the positives into positive aug, which have the same source image for the augmentation as the anchor, and positive dfsrc, which have a different source image for the augmentation. During representation learning, the BSC loss emphasizes the effect of positive augmentation more by utilizing balancing scales factor and multiple augmented images. So we describe the multi-viewed batch. Given a training batch data, we compose a multi-view batch like this. So M is the number of multiple augmentations. So instead of just one augmentation, you see we have multiple augmentations for each source. For an anchor J, the index for J sub M, the major component within the multi-viewed batch are like this, that we have positives augmentation, positive dfsrc, and the negatives. But we define this softmax based function, and here h sub j, here h sub j is defined like this, and z is the encoded feature of input x sub j by feature extractor f theta. And H is just a nonlinear projection network that maps the presentation to the space where contrastive loss is applied. We use the expression H sub j instead of H sub j and theta and phi. And tau is just the temperature hyperparameter. So finally, a proposed BSC loss for the feature extractor is like this. That we use projection of features instead of features themselves. So if we use projection, the network is prevented from being biased toward the current data set, thereby expanding the generality of features. Fine-tuning for domain knowledge transfer. After pre-training, our focus shifts to training the model to acquire specific domain knowledge relevant to the dataset. To achieve this, we add a fine-tuning process, since the feature extractor trained using equation 4, this one, prioritizes generality over domain-specific knowledge. However, training networks with large amounts of base session training data can lead to poor generalization and overfitting. In order to further enhance the generalization of learned representations, we adopt this CSKD loss and modify it for our multi-viewed augmentations. So it's just a KL divergence. So before updating the entire network, we initialize the classifiers for each base session class as the average vector of the corresponding class features. So the entire network is fine-tuned using this loss. So we have two losses, and we have a hyperparameter that is a trade-off between different two losses. You can play with this lambda hyperparameter. For the incremental sessions, as we said, we have many sessions, and they're disjoint. We set the classifiers for the classes of the corresponding session as the average vector of the feature because calculating the average is very simple. Of course, I've seen some articles that use attention instead of just simple averaging. And the reason for using the mean feature vector is that a small training set size could easily cause overfitting if one optimizes the classifier from a random initialization. Note that this method does not require any further updates, which enables much faster adaptation to incremental sessions compared to methods that require updates in incremental sessions. Additionally, we demonstrate that utilizing pre-trained generic representations without further updates on incremental sessions leads to even better classification performance on the classes of incremental sessions than the methods that update the model on incremental sessions. So this is the overall learning algorithm. We have phase 1, which is for training, phase 2 is fine-tuning, and phase 3 is the incremental sessions training. And this is the intuitive analysis for the effect of adding new classes on the classification performance of base class. Base class accuracy denotes the test accuracy of base session classes after the training of the fine-tuning. After new init is the classification accuracy measured only on base classes at the first incremental sessions.